The next section we're going to talk about is hybridization. So before we get into this section, I want to caveat it with this. Hybridization is actually a very easy concept. You will actually be hoping I ask you a bunch of hybridization questions on the exam. It is that easy. But to understand what it is, we're going to have to unpack it a little bit. So as I unpack it, if you're getting confused, don't worry, it will all make sense in the end. To understand hybridization, you should have already watched the video on valence bond theory because that's going to come into play. So keep that in mind. So what is hybridization? Well, when you hear the word hybrid, you probably think of, like a car, right? A hybrid vehicle. Well, the idea of hybridization is you are mixing things. So when it comes to a hybrid vehicle, we're talking about it has both elements of a combustion engine as well as electric components, right? And so hybridization is just when you mix things. When we talk about hybridization in terms of molecules, we are talking about the process in which atomic orbitals mix in order to accommodate the proper number of bonding sites according to valence bond theory. And I say mix because sometimes students think that scientists do this. We are the ones that go in and do things to mix the orbitals. This actually happens on its own. The atomic orbitals mix or blend naturally. And they do that, like I said, to accept the correct number of bonding sites necessary for a particular molecule. This also happens because it ends up being lower in energy than what it would have been before. And so hybrid orbitals help us explain the bond angles for a particular molecule, such as trigonal planar, which was 120 degrees. So hybrid orbitals allow us to create these new shapes of molecules and thus new energies. So hybrid orbitals, as we go through, you're going to see that they are named and determined by how many s, p, and d orbitals are mixed. So as an example, and you're going to see how we figure this out, if I was to take an s orbital and then two p orbitals, the hybrid orbital that would be created is called sp2. So the name comes from just what was mixed. Reminder that for s orbitals, there's only one, right? There's only one orbital. A p orbital or p subshell has three individual orbitals like px, py, and pz. And then d actually has 5 orbitals, right? Remember that? Now you're going to see we don't actually use all 5 because it only goes up to using 2. But the idea is the name of the hybrid orbital that is needed is just simply based on what was mixed. So, and you'll see that it's directly correlated to the number of electron domains. So if I have 2 electron domains, I'm going to mix an s and a p to get an sp orbital. If I have 3 electron domains, I'm going to mix an s and 2 of the p orbitals to get an sp2. If I have 4 electron domains, I'm going to mix an s and all 3 p orbitals to get sp3. If I have 5 electron domains, I'm going to mix an s, all 3 p's, and then I need one of the d's to make sp3d. And then finally, if I have 6 electron domains, I'll mix the s, the 3 p orbitals, and 2 of the d to get sp3d2. Now, like I said, that probably makes 0 sense right now, but it will make sense once we go through some examples. Okay, so let's take a look at an example. So let's take a look at the molecule BeCl2, right? So BeCl2. And I'm not going to draw the lone pairs on the chlorines. Not going to waste time doing that. Okay, according to what we learned in valence bond theory, in order for beryllium to bond to chlorine number 1 and chlorine number 2, beryllium is going to need a half-filled orbital. In fact, it will need 2. It's going to need a half-filled orbital to bond to this chlorine, and then it'll need a half-filled orbital to bond to that chlorine, right? Well, if I were to draw out the configuration for beryllium, right, it's 1s2, 2s2. We don't care about the 1s2 because that's not going to bond. It's always the valence shell that bonds, right? So if we think about the 2s2, okay, you've got the 2s2 and that one orbital, and it's completely filled with electrons because it's got 2. So that's shown right here. Now the 2p you notice is shown, but obviously it's empty. There's no electrons there. Now that's shown there for a reason. You'll see in a second. Does beryllium right now, according to valence bond theory, have the capacity to bond to 2 chlorines? No, it doesn't at all. Because remember, according to valence bond theory, beryllium would need a half-filled orbital for this chlorine and a half-filled orbital for that chlorine in order to overlap. Beryllium doesn't have any half-filled orbitals, right? It has the s orbital that's completely filled, and then these are all empty. So right now, beryllium is not looking like it can bond. But in all reality, beryllium does actually bond to two chlorines. So how can we explain why it does that? Here's what happens. It happens through the process of hybridization. So what ends up happening, and this, like I said, happens on its own, we don't do it, is this electron right here ends up moving or getting promoted to this empty p orbital right there. So that's shown right here. Okay, it moves that one electron. And then what happens is that s orbital and that first p orbital there, they actually mix together. So those two orbitals are going to mix. Okay, so what did we mix? We mixed an s orbital and one of the p orbitals. So we end up getting the hybrid orbital of sp. And what I want you to note there is it's not just one, it actually creates two of them. So that's what's shown right there. These two sp orbitals are created right there. I like to think about it like this. Imagine you're in the kitchen, you're creating something. So it's like you get your pot and you grab your ingredients. You're like, okay, I'm going to throw in an s and I'm going to throw in one of the p orbitals and I'm going to mix it up. Okay, and then I'm going to dish out two equal orbitals. Both of them are sp orbitals. I've created hybrid orbitals. As a result of doing that, I have now created, like I said, these two orbitals right here. They're both sp orbitals. This one has the one electron in it, and this one has the one electron in it. Now you have two orbitals that are half filled that can now overlap with the chlorines that are in the terminal position. So that was a process of hybridization to create. You now have these sp orbitals, and then these p orbitals here just weren't used, and so they just are sitting there. They were not mixed. Let's look at another example. Let's look at the molecule CH4, which is methane. So you have carbon that's bonded to 4 hydrogens. Remember, according to valence bond theory, in order for this carbon to be able to bond to these 4 hydrogens, carbon has to have 4 half-filled orbitals. It needs to have 4 orbitals that have 1 electron in each so that it can overlap with the 4 hydrogens. Well, if we take a look at the orbital diagram for carbon, which is shown here, how many half-filled orbitals do we have? We only have these 2. That's not enough, right? We need 4. So what happens is one of these electrons in this s orbital gets promoted to the next empty spot, which would be right here. So as a result of that promotion, we now have the s orbital and the 3p orbitals looking like this. What ends up happening is we take those orbitals and mix them together. And what are we mixing? We're mixing an s, and how many of the p orbitals are we mixing? All 3. So what hybrid orbitals do we end up creating? sp3. And look at that. We have created 4 equal sp3 orbitals. This orbital will bond to the 1 hydrogen. That'll bond to the 2nd hydrogen, the 3rd hydrogen, and the 4th hydrogen. So that's what ends up getting created to now make space to bond to the 4 hydrogens. Let's look at one more example. Thinking about PCl5. Okay, PCl5 is going to look like this. You've got your 5 chlorines. There's no lone pairs, so it's all chlorines there. All right, I have not drawn the lone pairs on the chlorines just to save us some time. All right, in order for phosphorus to be able to bond to 5 chlorines, how many half-filled orbitals does it need? If you guess 5, you are right. Well, if we take a look at phosphorus, its orbital diagram, right now it only has 3 half-filled orbitals. That's not enough. We need 5. So this 1 electron here is going to get promoted to the next empty spot, which actually ends up being not the 3p, but the 3d. It's empty right now, so it ends up getting promoted to the next empty spot, which then ends up creating this. We are going to mix the s, all 3 of the p orbitals, and 1 of the d orbitals, which then ends up creating sp3d. We have now created 5 equal half-filled orbitals that are all called the sp3d hybrid orbital. And it is these 5 orbitals that are going to overlap with the 5 chlorines that are here in this molecule. So as a reminder though, hybridization, so now we understand what hybridization is, and we understand the naming convention hopefully of, sp, sp2, and so on. But bringing it back to what I said earlier, the hybrid orbital that's needed comes directly from the electron domain geometry, or just simply the number of electron domains. So if you know that there's 2 electron domains, it'll need the sp orbital. And you can count on your fingers. Sp, that's 2. If it's 3 electron domains, sp2. So that's going to be the hybrid orbital there. If it's 4 electron domains, it's sp3. Now, for 5 electron domains, you can't say sp4. There aren't 4 p orbitals. So you'd say sp3d. And then finally, 6 electron domains would need an sp3d2. And so, like I said, we actually only use, that's as high up as it goes. There's no 7 electron domains. So sp3d2 is the highest hybrid orbital that you would need. All right. Let's do some examples. So example number 5, I have 4 molecules here that actually we've done these molecules before. So in your printed notes, you should have these structures already drawn in previous areas. Water is a common example, but to determine what hybrid orbitals are going to be needed, we need to first figure out how many electron domains each molecule has. So if you recall from water, how many electron domains did water have? There were 4. And I'm not going to draw this out for every single one, but just as a quick reminder, this is the Lewis dot of water. There's 1, 2, 3, 4 electron domains. So what hybrid orbital is needed for 4? sp3. That would be the hybrid orbital that's needed. What about SO2? How many electron domains does SO2 have? If you remember, there were different ways that you could draw SO2, but doesn't matter, no matter which way you draw SO2, there are 3 electron domains. And so that would need the sp2 hybrid orbital. For BRF5, okay, that was in a previous example that we did earlier on in this topic. So if you go back and take a look at what was that Lewis dot, remember, and I'll draw this one just to remind you that it's so important, you have to draw the Lewis dot because you end up getting the 5 fluorines, but then remember there was a lone pair there. So how many electron domains are there? 1, 2, 3, 4, 5, 6. So because there are 6 electron domains, that's going to need the sp3d2. And notice that the numbers are written as superscripts. Okay? Sometimes students write them as subscripts. No, we write them as superscripts, or exponents if you think about it like that. And then finally, XEF4. If you take a look at that Lewis dot structure that you drew earlier, how many electron domains does that molecule have? That has 6 as well. So once again, it's going to need sp3d2. All right, that wraps up our section on hybridization. One more section to go for topic 7, and we are all done. We'll see you in the next video.